So I will just briefly introduce, well, Sarah, who's not here, but Marc, both architects at AGPS, a firm with ateliers in Los Angeles, Zurich, and Prague. Their projects done in collaboration with their partners, Manuel Scholl and Matej Dressler, and many other collaborators, include the headquarters of the International Union for Conservation of Nature near Geneva, the Children's Museum of Los Angeles, the aerial tram in Portland, the Zurich International School, and the Midfield Terminal at the Zurich airport, and several other housing projects in Switzerland. They received several awards from the AAI for their off-the-grid branch near Santa Barbara, which is a recent project. Both Sarah and Marc have taught at several universities, including the Harvard Graduate School of Design, ETH Zurich, and University of Southern California. We're very happy to have Marc present some of the work today, very much revolving around this topic of Mercury Rising and architecture beyond greenwashing. We will also have, as a respondent, Alia Bengana, who's anyone who's at EPFL is familiar with. She's a French-Algerian architect, teacher, and journalist, awarded a grant from the American Institute of Architects in 2006. She founded her own office in 2009, and in the past 12 years has been specialized in the use of regenerative materials, earth, and fibers, with a particular interest in available resources, and now teaches at EPFL in first year, and has agreed to be Marc's respondent. So we'll be looking forward to that. And then we have also two of our own RIOT students who will be also joining the discussion afterwards. Marc, please, the floor is yours.
Well, thank you very much, Charlotte, for the kind introduction. It's a great pleasure to be here at the EPFL also, and to be given the opportunity to see the student work today. It was a very exciting morning and afternoon. And I'm also greatly looking forward to discuss with you the propositions that I have received from the faculty, absolutely radical proposition, brilliantly written. I've received this a few weeks ago, and the statement opens with a provocative question: isn't construction unsustainable by design? A question undermining the very essence of what we have been doing as architects and what we do as architects. So this is an arrow going straight through the soul. The second paragraph is rather pessimistic, but there is an optimistic moment in it, calling for actual change towards less emissions. So this already tells you the direction in which we should go. Followed by the third paragraph, asking how, three times, how to do that, how to face the mistakes of the past, to identify new trajectories grounded in humility, beyond greenwashing. The last two words are beyond greenwashing. So much for Mercury Rising. I would like to do so I would like to address this statement by the faculty by addressing the ambivalent role of technology that is being deployed today in environment making practice, as depicted in this illustration from a 2011 cover for The Economist entitled "Welcome to the Anthropocene." Whether called Anthropocene, Urbicene, Capitalocene, or Technocene, we have undoubtedly altered the face of Earth. Shown here as a technical contraption in the process of being put together and taken apart, a form of geoengineering or geoarchitecture operating at the global scale. This is the status quo condition. This contraption is unsustainable, to say the least. Any effort to fix the situation, some argue more technology is needed, a techno-fix, so to speak, to mitigate the negative effects of our actions on world climate. This takes me to the theme of my lecture, namely the role of the technical systems deployed to create environments for habitation. In this case here, a recent building in Switzerland, a 7-story structure with workspaces and dwellings above, cooled by river water and heated by the city's heating grid, powered by the municipal waste incineration plant. In short, the pyrotechnics deployed today to not only create environments for habitation, but also habitats that, appearances to the contrary notwithstanding, would minimize the impact of architecture on climate. Mind-boggling is the amount of technology needed to be sustainable. Each small dot represents a switch connected to other components, which are connected in turn to other systems, a machine in its own right, and a far cry from the call to be truly sustainable. My lecture is hence entitled HVAC, heating, ventilation, and air conditioning, plus water and sanitation systems, plus electricity and information technology. And is subtitled Beyond Architectural Pyrotechnics, a term coined by the Indian architect Charles Correa. These are the technologies that infiltrate our work these days, despite our suspicion vis-à-vis anything technical. We cannot simply push them aside in an act of psychoanalytical repression if we intend to address the how to recalibrate the relation between architecture and its host environment today. So to walk the talk, I have organized my intervention as a shop talk on how we as architects today, as architects in practice, how we have tried in the past and how we try today to overcome the dilemmas associated with sustainable construction, And we'd like to share some projects done in our Los Angeles and Zurich ateliers, understood as sites of architectural production, and foreground the struggles encountered when trying to act sustainably. This is a story about failures from which we successively tried to learn. Or, in the words of Samuel Beckett from his 1983 satirical novella, Worst Ward Ho, ever tried, ever failed, no matter, try again, fail better. The good message for the students. The question, however, is and must be raised whether we still have the time to fail. Our story of failures is actually the subject matter of our recent book, Flux Redux, 9 Sites of Experimentation in Stocks and Flows, that opens with backwards quotes on our ability as architects to fail better. A book written in collaboration with my partners, Manuel Scholl, Sarah Graham, and Matej Drasler, who is with us here today in the audience. The book includes nine cases covering a period of 30 years, starting in the late 1980s and ending today. Important in this sequence is how our focus shifted over the years, from an obsession with reducing the quantity of energy needs for operations at the beginning, to the quality of that energy, and subsequently to the embodied energy associated with materials used in the later work. So 30 years and change of ideologies throughout these 30 years. In all cases, technology, even when reduced to a minimum, played a significant role when trying to move towards a new paradigm. I have selected 5 cases. Oops. How do I go back? I have selected, of these 9 cases, I have elected 5, which I would like to share with you. The town center outside of Zurich, then the Zurich airport, then the ICN headquarters not far away from here in Cologne, the Guggenheim Helsinki, the aborted Guggenheim Helsinki project, and the recent ranch that Charlotte mentioned that was finished a year ago. But before I start, 3 quotes representing fundamentally different positions on buildings as complex assemblies, or more precisely, as complex machinic assemblies. So first quote that you see here on the screen is by architectural historian Rainer Benham, who, by the way, also studied mechanical engineering. He wrote a short essay in 1965 entitled "A Home is not a house. Banham Essays opens with a laundry list depicting the building as a machine, an inhabited machine in the Corbusian sense, albeit minus the house. And he writes, when your house contains such a complex of piping, flues, ducts, wires, lights, inlets, outlets, ovens, sinks, refuse disposal, hi-fi reverberators, antenna, conduits, freezers, heaters, when it contains so many services that the hardware could stand up by itself without any assistance from the house, why have a house to hold it up? The text is accompanied by the drawing Anatomy of a Dwelling by French-Canadian artist François Dallegré, showing the systems that comprise the home that is not a house, while creating a fit environment for human activities. Banham and Dallegré, in short, revered or even fetishized anything technological as an emblem of progress, in what Banham would later call the machine age, whether first, second, or third. Second quote. A fundamentally different approach is proposed by Charles Correa in his 1980 essay, Form Follows Climate. Form Follows Climate. Surprisingly, he also talks of the building as a machine, though a machine of a very different order. From the vantage point of a practicing architect working in India, he writes, in the absence of sophisticated mechanical technology, so he's operating from a tropical climate, okay, a developing world, it is the building itself which must create the controls the user needs. The house as a machine for living. Controlling climate by means of, and here comes his list, verandas, terraces, courtyards, overhangs, intermediate zone, cross ventilation, the Venturi effect, solar energy harnessing, trees for shading, water as humidifying element, using space as a resource itself. Correa illustrates his idea with a section of the Red Fort at Accra, showing a sunken courtyard above which a horizontal curtain is being stretched in the morning to trap the cool overnight air. So this is a sunken courtyard, and here's the velvet curtain that is being stretched to trap the cool overnight air while providing shade during the day. In the evening, the curtain is removed to be then replaced in the morning again, and so the cycle continues. He moreover extends his argument to the way users use the building in cyclical patterns of habitation. Correa makes a plea in favor of an energy passive architecture with architectural elements to control a space's microclimate. Elements that could also be considered a type of technology. So architecture as a kind of technology, albeit a technology minus mechanical systems. Architecture does the job and its form follows climate. Third quote is found in a 1984 essay by Alvaro Siza entitled Living a House. Surprisingly, Siza also depicts the house as a machine, yet this time as a machine that breaks down and that needs to be repaired. He writes, and listen to the list again, the idea I have of a house is that of a complicated machine in which something breaks down every day, a lamp, a faucet, a drain, a lock, a hinge, a socket, and then the heater, the stove, the refrigerator, the television, or the video plater. And after that, the washing machine, the fuses, the curtain springs, or the security bolts of the door. And the students have read this essay, and the list continues forever. The text proceeds by stating that living in the house brings with it the added measures of maintaining and repairing the constructed realm we inhabit to truly live the house. The text is illustrated by two sketches he made while visiting Le Corbusier's La Petite Maison, not far from here, built in the 1920s, so 100 years ago, that's not bad, which has since been constantly maintained, transformed, upgraded, restored, and even outfitted with a new facade and an addition on the roof. Caesar's reflection could be read as a parable about stewardship, one that is timely in that it bears on our relationship to the built and natural environment today. He asks, are we not in a constant repair mode in every matter we face? His call for living a house, or by extension for living the environment, underscores the care required to sustain any architecture of habitation. So let me move on to the cases which oscillate between Banham, Korea, and CISA's propositions. Besides being machinic assemblies of different sorts, what is coming to the projects, each approximately 8 years apart, is the objective to reduce the environmental impact, aware of the fact that form affects climate. So let me take you to the year 1989 and to the Esslingen Town Center on Zurich's periphery under the heading Pioneering Pioneering Errors. The competition brief included this postcard of the community situated in magnificent landscape with rolling hills, agricultural fields, patches of forests, and waterways lined with trees. What could also be seen were the first signs of sprawl encroaching on the otherwise bucolic setting. So in the meantime, sprawl has taken over. The brief proposed to cover the existing creek cutting across the site. So this was the site and this was the existing creek, and the owners of the land wanted to cover this creek. Opposing this idea from the outset, we took the risk to organize the entire scheme around the creek. The main components of the projects are, on the left, the public buildings, a light rail station, community restaurant, post office framing a square. In the middle, buildings with workspaces following the creek. And on the right, the dwelling units organized as row houses, though that would later change. So there were 3 different clients for this project. For the public part, on the left, the community, represented by the mayor, who believed in the project. This was very important that we had the mayor on our side. For the workspaces, 2 senior engineers who would evolve to become the patrons of the project, and a housing cooperative that was enthusiastic but did not have the means to build the project. In the model that you see in the next slide, the public spaces are located at the highest point of the site, and the sequence of buildings following the topography along the waterway are seen in this portion. So this is the square, the train station, the restaurant building, the post office. A novelty at the time, the brief asked the participants to be environmentally conscious. Okay. We never heard that before in an architectural brief in 1989. This was revolutionary. The project thus evolved into a study on how to make architecture ecological before really understanding what this would entail. A way of doing without knowing, but at least with a hunch. We decided to use the sun as energy source and propose solar collectors on the roofs and a Tron ball on the vertical south-facing surfaces. Here, a view through the Tron ball capturing solar energy passively between an external and internal layer, while still allowing views to the Alps beyond. So far, so good. We won the competition and started to work with the 2 senior engineers that were the mentors of the projects on a manifesto that would become a roadmap for the first building along the creek. By the way, we did not know the term sustainability at the time, and used instead the complicated expression environmentally minded household management of resources. So this became the important point. The 11-point manifesto put forth a series of action points, including the need to integrate buildings in the natural environment, to encourage multiplicity of uses, to use passive and active solar energy and natural light, to encourage the use of recyclable building materials, also with the idea to create a market for recyclable materials, and then lastly, to increase the lifespan of building materials. As this sounded abstract, we asked the engineers to visualize the mandates, and they came up with these 3 diagrams. The first concerns the amount of energy used, comparing a status quo building with Swiss targets and benchmarks for our building. White represented the solar gains. So this was the SER targets, this is status quo, and this is what we needed to achieve with the building, whites representing solar gains. So let me move back and forth again, sorry. The second diagram showed the lifespan of components, 150 years for the structure, 60 years for the facade, 30 years for mechanical systems, etc. So the lifespan varies on different building components. And the third diagram rejected demolition and argued in favor of recycling approximately 90% of the materials. Okay? This was an unbelievably optimistic objective. At the same time, our team did the same thing, so drawing diagrams, translating the targets into sections, showing the trompe wall on the far left, including energy storage in an interior wall, the concept of energy recovery in the middle for the housing units, and concepts for ventilation and heating on the right, fueled by wood pebbles for the few cold weeks of the years. So simulations showed that the trompe wall was an absolute disaster, overheating the building. Heat recovery made little sense, as we had to wait 15 years for the housing to be built. It was nonetheless realized. And then when the housing came, it was antiquated. And efforts to convince the user to not build a heating system and simply wear sweaters failed. As cooling and heating became important, horizontal tubes were introduced below the building to use the constant ground temperature for cooling, approximately 5 meters below ground. Regarding the durability of components, the facade was built using demountable layers without glue. Elements with the longest lifespan were placed inside and those with the shortest outside. For the facades, local timber was used for the facade and the roof. The elements were prefabricated in local workshops and then mounted in situ. Shredded recycled paper was used as insulation material built in the prefab panels. Here 2 images of the enclosure showing the movable brise-soleil panels that then replaced the trompe wall that could also act as light reflectors to reduce electricity needs, and the scaffolding used as a stage for cleaning and for repair. The images showed the first phase of the project with the rail station on the far right, bus stations on both sides, the post office, bicycle stands, and the first building along the creek. It took, however, and it was empty. It was empty for years. And it took about 15 years for life to take hold, for the vegetation to grow, for the housing and the kindergarten to be realized, and the next buildings along the hill, down the hill, along the creek to be built. All in all, what we learned from this experiment is that we still relied on too much technology to try to be sustainable. So this is lesson 1. This takes me to the second case from the late 1990s, the airport terminal in Zurich under the heading stripped down. So we had this heading in mind already at the time. So let me start with this section here, which shows you the entire story, a comparison between Richard Rogers Terminal in Madrid in light blue and ours in dark blue, built at the same time with the same number of gates for the same number of passengers per hour. So same functions, absolutely same functions, different volumes. Ours with less volume, less energy needs, less material deployment, in line with the public client's sustainability mandate. So this was also in the brief, notwithstanding that a sustainable airport is an absolute contradiction in terms. The initial step was to assemble a team of architects, structural and mechanical engineers, and cost estimators, including psychology as coach that you see here. So she was a member of the team to make sure that the different disciplines and different age groups would indeed talk with one another. She was the most important person in the team. She suggested that we should communicate ideas not only verbally. I mean, architects have always a difficulty to express themselves verbally, engineers even more so. So she said, do it visually, using various images, sketches, diagrams, and the like to communicate. And the first images on the table were recently built airports, be it in Osaka, Hong Kong, or Kuala Lumpur. These airports look surprisingly all the same, despite their pretense of being uniquely spectacular. They were formerly exuberant, superficial, overscaled, disorienting, and overly commercialized. They were all the same. I mean, we went and visited them, absolute horror. This led to a discourse on form within the team and to the decision to pursue a project without form. So, no form. As for technology, the engineers would have to aim for less and less mechanical systems. This was their mandate. So we said no tech as the key maxim for the mechanical systems. This with the idea in mind to reduce greenhouse gases, at least for building operations. We are early on in our thinking, so building operations. So no greenhouse gases for building operations. At the end, we had a lot of everything, though it was a good point from which to start the process. The team looked at no-frills infrastructure, including Marilyn Reese freeways in Los Angeles. Why not simply build a piece of freeway, a double-decker, 500 meters long, and design an airport as naked as possible? By the way, an expression by Le Corbusier, a naked airport. This led to a formless building, an undecorated shed, reduced to the max and based on the premise to do less with less, its boring appearance notwithstanding. There's nothing wrong with being boring in terms of form. For the structure, we worked with this image of a house on stilts, not far away from San Francisco, that we squeezed and multiplied many times to get a sense of the substructure anchored in the bedrock 50 to 70 meters below ground. And what you see on top at the end, the terminal, is nothing else than the tip of the iceberg. The piles were used in collaboration with the engineers and the structural engineers and mechanical engineers to heat and cool the building. In effect, harvesting the energy in the ground, cooling in the summer and reversing the system for heating in the winter without using fossil fuels. A model photograph shows the building sitting de facto not on the tarmac level. The tarmac level is this one here. So this is where the airplanes are, but on the sloped bedrock below. So all these vertical lines are the piles to anchor the airport on site. The construction piles determines the placement of columns above. So there was a relationship, and vice versa. The bigger the span above, the less foundation piles below, the less energy could be harnessed. So there was a kind of effect, one affecting the other. The section shows that both passive and active systems were used to minimize the resources for building operations. So the geothermal probes at the bottom, active and passive, the thermal buffer zones on both sides, kind of a double skin as a sweater, passive. The Venturi effects in the light cores up here, natural ventilation, passive. Decentralized air units without ductwork. So here, wherever we had a spot, we put these units. So without ducts, but active. Photovoltaic shading elements on top on this pergola, active and passive, and a maximum of daylight to reduce electricity loads for the entire building, passive. A few images of the completed building. First, the solar panel pergola on the roof, the unheated buffer zones that you see here with the ramps to access the planes, and the departure level punctuated by air ventilation cords that you see here. All materials are exposed. Nothing is covered. What you see is what you really get. So if you knock on the walls, it's not hollow. An analysis of the building made after completion, comparing terminals, showed that we indeed managed to reduce the operational energy needs per year. So we are the last bar here on the side. and the biggest gains in red for heating, in this case here, of the building. So this was a success. Nonetheless, lessons learned from this project is that we would need to shift our focus in the future from a focus on operational energy to the materials embodied energy. I mean, the amount of materials we used for this airport was mind-boggling, was crazy. Okay? In German, you say Materialschlacht. Okay? So this is what we got. So this embodied energy became an obsession for us, the energy that is required to produce construction materials and products. This is standard practice these days. So this is what we try to do with the next project, the headquarters addition for the International Union for Conservation of Nature in Cologne, under the heading Balancing Performances. So keep this in mind, that we are balancing performances. So IUCN, International Union for the Conservation of Nature, has since evolved, since the 1940s when it was founded, has evolved into the world's largest environmental network with ties to the UN, an organization dedicated to safeguarding the natural environment. So founded after the Second World War and up to now still operational, and they are dedicated to safeguarding the natural environment. Policy making is what they do. Okay? So they are policy makers. They have been key players in what could be called global climate governance, initiating the red list of threatened species from the 1960s. So the team today working with non-human creatures in our environment should read this manifesto. So this is from the 1960s, but they also contributed to such pacts as the Brundtland Report, the Rio Agenda, the UN SDGs, and most recently, the Paris Climate Agreement. Since IUCN is in the business of policymaking, their building had to comply with every possible labeling standard. So we had to go through every possible label standing. Well, obviously the Swiss Energy Code, Minergie P Eco, then LEEDs, okay, the LEED rating system, the European labels, European Union labels, among others, such as the Green Mark for Singapore and the Green Star from Australia, that is now also used in Vietnam and in Africa, mostly in South Africa. At the end, we focused on those first three. All these labels are made of hundreds of indicators, which, as we found out, contradicted one another. This was to be achieved. So this was the objective, satisfy the three first, but this has to be achieved with a minimum of money, a minimum of financial resources. Available money would have to go to safeguarding endangered species rather than being spent on a building. They were not interested in the building. Okay? They had another objective. Elephants over architecture became the operating axiom. So basically, no money. To reach the labeling standards, the team had to balance the environmental performance of components. So this is where balancing performance comes into the game. Planting an additional tree, even in the garage, gave us an extra parking space. Recycling concrete from demolition sites permitted the use of a synthetic rubber membrane. Greening the roof of the existing building increased the site's water retention capacity. Waterless urinals compensated for the ecological impact of kitchen appliances, and using wood for the facade, oops, sorry, I went a little bit too fast. Using wood for the facade in this last image allowed us to increase the amount of glass, which in turn reduced electricity needs and so forth. And this was summarized in chart that you see here, essentially forcing us to design by numbers. So each time you put something in, it was calculated. You said you can do this, but you can balance it out by doing something else. A meeting with the cook, which didn't give us any points for the LEED standards, the cooks of the canteen proved to be beneficial in this regard, considering that the amount of energy associated with incoming food and its preparation was astronomical. So the menu had to be redesigned, and I was sitting with them redesigning the menu, putting a premium on local products, using less meat and offering non-heated dishes. And here a photograph of the existing building from the 1980s that was conceived as a hermetically closed box for the purpose of saving energy and without any connection to its context. And for the addition, we decided to turn the principle inside out and basically switch what was an inside outside. So this was the concept for the building. And now in the model, the extension here in white was conceived as a mat building, punctuated by courtyards and surrounded by a veranda to passively shade the facades. And a series of diagrams: green, the heated spaces; yellow, the outdoor courtyards; blue, the internal double-story spaces; red, the cores; and purple, the veranda as emergency egress and buffer between inside and outside. Do I need to respond to this? No. So the roof was articulated as a shed with skylights facing north and hybrid collectors, a combination of photovoltaic and warm water collectors facing south, hovering above the conference room. And here in the next image, the conference room overlooking the collectors with views of Lake Léman and the Alps beyond. A few words about the mechanical systems that you see here in a diagram. The heart of the system is the heat pump that you see here, which is connected to 14 geothermal probes going 250 meters deep into the ground. These are linked to the roof collectors, since we have hybrid collectors above that produce electricity as well as heat, the latter being stored in the ground, understood as a seasonal energy reservoir. The heat pump in turn is connected to decentralized air boxes along the facade, heating or cooling the incoming air, and no ducts are required. These in turn are activated by CO2 sensors on the ceiling. Air exhaust is passive, here seen in double-story spaces, and lastly, a water tank collecting rainwater to flush the toilets. Moreover, the team collaborated with the concrete industry, testing various applications, reusing crushed concrete from demolition sites, thereby recycling concrete, successful, reducing the amount of CO2 content of concrete, less successful, and increasing the insulation value of concrete, partially successful. The construction is a hybrid of combining timber for the facades and roofs and concrete for the primary structure, with a minimum of steel where needed. In the next slide, a view of the completed project seen from the entry courtyard situated between the existing building on the right and the addition on the left, and an external photograph showing the main courtyard in the center here, and the balcony circumscribing the building, and a view into the courtyard a few years after completion, which turned out to be the most important space of the ensemble. One additional remark concerning the approach to on-site landscaping. Instead of designing an attractive garden with landscape architects, we worked with biologists and botanists who basically decided to leave the landscape as is. So they said, don't do anything, with sheep from a nearby farmer maintaining the premises when need be, an approach requiring a change of mindset for all parties involved. Okay? And I can tell you our landscape architects were not happy about this. After completion of the project, an environmental impact assessment report was prepared to check how the building was really performing. This chart shows the quantity of energy used per year, comparing a standard building with ours. So here's ours, and this is a standard building. So far, not bad. We were very happy. But then when other components are brought into the picture, such as the energy used for furniture, IT equipment, commuting, and air travel, it became clear that air travel far outbalanced the energy that went into the entire building by a factor of 4. Okay, it's an international organization. They had to fly constantly to Nairobi or to New York. In any case, IUCN had to change its practices. Okay? And I would say that the pandemic helped tremendously for this. Allow me to show you another metrics at the risk of sounding like a nerd, one concerning the quality. Okay? Before I show you the quantity, now I'm showing the quality of energy measured in kilograms CO2 per annum. Okay? Revealing is that we used more embodied energy for the materials in orange than the standard building. I mean, this line is higher. And we used also more technical installations in gray. So from this to this, in order to reduce operational needs. So more technology and more materials in order to achieve this reduction in CO2 emissions. Partly also due to satisfying too many labeling standards that were contradicting one another. Now translated in square meter emissions, the building required 12 kilograms CO2 per square meter per annum, a calculation taking the lifespan of building components into accounts. And when you include daily commuting, the number goes up. And when you include air travel, okay, all gains are lost. I mean, this is an unbelievable number. By the way, kilogram CO2 equivalent square meter per annum is the new unit. Okay, we have to become, as architects, we have to know this unit. Okay? It is the new unit to deal with in architecture. So square meters we know, kilograms CO2 we can understand. Equivalent means it addresses other things. Per annum is also clear. So everything is in there, also including replacement of parts. What we learned from this exercise is that current energy labels supported by lobbies in the construction sector, okay, there are lobbies behind them, don't forget that, are often counterproductive, leading to more material and technical deployment to be sustainable. So from then on, we decided to go our own way, okay, and we criticized publicly and politically these standards. So let's move to the next case, from the mid-2010s, our entry to the Guggenheim Helsinki competition, which was awarded second prize, here under the heading On the Grid. Yeah, so that's its title, since we conceived of the building as a public utility. So the aerial view shows the existing ferry terminal that you see here. This was the site for the building, and it was to be replaced. So this ferry terminal had to be replaced with the Guggenheim Helsinki. The chosen terminology being rather revealing. First, a global player who wanted a new museum but did not want to pay for it. And second, a city that did not really want a museum but had to pay for it. Now, taking this predicament to heart, we did three things. One, we engaged in discussions with activists who were against the museum. Two, we treated the Guggenheim as an interim user, considering its history of failed museums. And three, we entitled the project "Ceci n'est pas un musée." This is not a museum. And we were selected to continue to work on the project. Our scheme was simple. We kept the existing terminal and added a box on top, a sketch, by the way, done by Matej Drasla very quickly on the desk. Okay? So this is what you see here. And then here's the box and the terminal and the box in the model, okay? Here in this location, a model done by Frederic Hans, who is one of the junior faculty members here at the school. And I think he's online somewhere in Kyoto watching. The submitted sustainability report. So we had to submit the sustainability report, comprised 3 pages. Okay? The first page made a plea to reuse the existing building, the Makassini terminal, as it was called, taking the existing building as a resource of embedded energy. In line with Lacaton Vassal's statement, never demolish, never remove or replace, always add, transform, and reuse. The second page addressed the notion of a full zero concept, not net zero, which has evolved into one of the biggest corporate lies imaginable. And for this, we presented a formula which read embedded energy in the construction, okay, the existing building plus our new, plus operational energy, this is what happens every year, equals 50 years of energy production by the building. By implication, the older the building, somehow it's stuck. By implication, the older the building, the smaller its ecological footprint. Measured in kilogram CO2 emissions, this meant that the construction was initially using 15 kilograms CO2 per square meter per annum. Okay? So this is where the biggest amount of energy is plugged in when you build something. And you would need 50 years to get to zero under the condition that the building produces more energy than it needs. Okay? So you have always a surplus, and with this you compensate what you've put in terms of energies for the materials and products. This revealed that Helsinki's objective to reach zero by 2050 was off by 20 years, if not more. And I know we had long discussions with the mechanical engineers whether this would be 70 years or 80 years, okay? And at the end we said, come on, it's a competition, push for 50. The third page outlined how we would do that by plugging the building into existing municipal grids using their storage capacity. Okay, so the storage energy is becoming more important from project to project. So so plug the building into existing grids using their storage capacity. First of all, the cooling grids that used harbor water to cool buildings existing, newly built. The electrical grids to feed electricity into that grid and drawing from it, which has become a standard. Okay? And I just heard in California that this will not be allowed anymore. That means we will have to have batteries, which is totally stupid. And then the heating grid, in which we would feed emission-free energy instead of using energy from a nearby power plant that used coal as a resource. Okay? So basically, we said no coal. Coal, by the way, imported from Russia at the time. In this axonometric drawing, the various components of the building, the ferry terminal below, the primary structure in timber, above that, the box also in wood, and the skylights and collectors above. The layered building here in the model, which also Fred can build with the public spaces at ground level and the enclosed spaces above, and situated between the harbor water below and the sky on top, both used as resources and being at the core of the energy commerce. The water and the sky were key resources for the project. Lastly, a view across the harbor toward the project, simply a line on the horizon. It was one of the projects of these unbelievable amount of entries that were produced that had the least form to them. So just one line. Lessons learned. Okay? To get to zero, you need to produce more energy than you consume. That is not any kind of energy, but as emission-free energy as possible, while not less trying to reduce what you consume. You need to reduce that in any case. Let me end with a recent project, a ranch in the California countryside under the heading off the grid. So the previous one was on the grid, and this one is off the grid. The project, or more precisely, the entire ranch, is off the grid and almost self-sustaining. The building is comprised of several habitable spaces surrounded by terraces, all under one big roof facing south for shading, water collection, and solar harvesting. An architectural critic called the building a machine in the garden, though as a matter of fact, it is rather the garden that is the machine. So let me focus on the garden and the site as a resource for the project. The main objective of this project was how to resource the site itself. Note the thin line here reaching into the ground. It is the project's umbilical cord to the aquifer. As a matter of fact, the most important machine is the pump connected to that line, accessing a 150-meter deep well for water supply and used to cool or heat the structure. So we are using the temperature of the water to cool and heat the building, taking advantage of the constant ground temperature of 16 degrees Celsius. Solar panels power the water pump and provide electricity for the entire ranch. Cisterns collect rainwater to replenish the aquifer. The compost recycles organic waste for reuse on sites. It's bigger than my apartment in Zurich. And septic fields, well, the septic fields here provide on-site sanitation for human waste disposal. Most important, every plant is eatable, ranging from vegetable, fruits, and peppers, very hot peppers, to crops for animal fodder. The ranch inhabitants, oops, I should learn to press only once. These are the ranch inhabitants, 12 humans, 16 horses, 3 dogs, 22 chicken, 3 geese, and 2 cats. Not to mention the assorted wildlife that wanders onto the premises. There are several buildings on site, among them a barn that was transformed into a habitable structure for ranch activities, keeping as much as we could and replacing as little as possible. Modifications were done with components resourced from on-site structures, okay, initiating a literal material dance across the facility, okay, including panels, walls, gates, and the like. Is anything moving? So material dance, whatever material we could find would be replaced for them. And some materials, however, had to be brought in from the outside. Okay, this is this arrow coming in for the kitchen and bath and for upgrading the structure and facade. These incoming materials were selected from agricultural catalogs. We have an entire collection of agricultural catalogs, among them FarmTech, a regional company with a yard close by, so we could go and see the materials, and they were offering products that are local, robust, functional, and cheap, including components for prefab barns, okay, which we use to upgrade the structure frame, or recycled plexiglass and fiberglass for the facades, and mylar for curtains providing thermal insulation, and multiple other components such as cables, tape, cardboard, light fixtures, and standard tubing. So extremely cheap materials that were assembled without fuss, no Swiss details here. You have to just bang it together. A few remarks about the activities that take place. First and foremost, the workshop. There's always something that breaks down and needs to be repaired in line with CISA's essay. And I would say this is the most important facility on site. Okay, yeah, I'm constantly there, you know, drilling or I don't know what. Furthermore, the space is used for cleaning and drying agricultural products because it's our operational ranch, for instance, on the left, or for storing hay on the right. Other uses include a space for sleeping, so for guests, for example, or for kids who call the building the schoolhouse during the pandemic to do their homework. The space is also used for community gatherings. As you see on right, the first communion, a Cinco de Mayo celebration, or recently a wedding party. If the Beamer wants to play with me. So this is the wedding party on site. So much for the cases. Right? Returning to our publication, Flux Redux, 9 sites of experimentation in stocks and flow, which includes the cases that I've shown and many more. The book ends with the following quote by Paul Virilio from 1996. He writes, "When you invent the ship, you also invent the shipwreck." So this is given. You invent the ship and then you have the shipwreck. Every technology carries with its own negativity, which is invented at the same time as technical progress. So you get technical progress, but you get exactly the opposite at the same time. So that said, let me conclude with the following propositions. So first proposition, in tech we trust, just don't. Okay? And I love to say that at the École Polytechnique Fédérale de Lausanne. Okay? In tech we trust, just don't. Go to any other department. They trust in technology. 2, as a matter of principle, technology will always fail. This is a given. Okay? So assume that as soon as you have technology, it will collapse. Okay? Don't underestimate its hidden costs, okay, or externalities, okay, i.e. its short lifespan. So technology has always a short lifespan. Its embodied energy, its operational resources that are required to make it work, etc. Use as little technology as possible. Okay? So don't put too much salt in the pasta, basically. And when obsolete, do not discard, instead repair. 5th, always consider its socio-technical ecological ramifications. Okay? Technology is always embedded in the bigger system, and also don't underestimate its underlying power dispositives, okay? The lobbies defining standards, etc. Lastly, whenever possible, use space as a resource itself because it's there. Okay? Making sure that form follows climate. Thank you very much.
Thank you, Marc, for the presentation and this honest view on questions of sustainability. And